Thank you. Hello, everybody. Thank you for inviting us. Yeah, now we will tell you a story about here we should be exploring possibilities for integration of StrictDoc with ELISA's requirements template approach for Linux kernel. And this is an immediate response to the talk from Gabriel we just heard. So they propose a rather tool agnostic approach with SPDX tags inline to the source code. Now we come and say, look, you can do this almost one by one by using StrictDoc as a tool. And in that regard, I'm very happy that Stanislav Pankevich, the maintainer of StrictDoc, has joined as a. And he supported very strongly during the last weeks doing this prototype. So thank you, Sven. Brief words of introduction. I'm Tobias Deiminger from Linutronix. You may know us best for our work on real-time Linux. I'm doing mostly security features there, and notably was, let's say, the counterpart of TÜV when we did security certification of our EGLOS operating system. And besides that, I like open source and contribute with some focus to StrictDoc and Debian.
Are you still with Linux? With Intel guy?
I didn't understand, sorry.
Are you still with Intel?
Yes, yes. May you introduce yourself?
Yeah, one more time. I'm Stanislav. I do flight software for the satellites in my day job, and in my spare time, I contribute to open source software, most notably the StrictDoc project, and also I joined some working groups, for example, the SPDX functional safety.
Okay, our agenda for today is 3 parts. Stan will give some general words about StrictDoc and requirements engineering. Then I will show you how we use StrictDoc internally at Linutronix. And then we come to the main part where we show you our experiment live on GitHub. Stan?
Yes, I would like to start my part of the presentation with a joke that has some truth in it. So every hard engineering problem can be solved with an infinite amount of cache. So how much cache is needed to bring requirements to open source software? And a few years I started my open source project to somehow tackle the requirements problem. And I got quite a mature implementation, collected some open points, some controversy around it. And quite frankly, I don't think that infinite cache is required to solve the requirements problem, but there are many controversial points that can kind of slow down the adoption. And I'd like to talk about the 3 aspects: culture, methodology, and tools. So before we actually talk about these 3 aspects, let's agree on what we mean by requirements in this talk. And I didn't have to go very far to find good requirements in Linux, and that is POSIX requirements. Okay, POSIX, there is some involvement with the standard library, but in fact, the open group website shows lots of requirements, and specifically, we have statements that are usually shell statements. In this case, we have a shell lock the semaphore, and then some other text, and we have rationals. POSIX specification has a rational chapter which says why something is needed, and in this case, we say that a new relative function, like sleep function, is needed to allow something else. So we explain why something is used. And then the third very important component is the UUID. The POSIX specification is really missing it. Ideally, each atomic statement is uniquely identified. This allows us to locate this, to pinpoint these items, and also link them with each other. So now let's talk about the culture. And
please move the. Yeah.
That one.
It's also like,
Sorry, that worked. The bottom part seems to be fine, actually.
Yeah, okay.
Just too close.
Oh, that guy's
Too close.
sorry, but I asked you.
Like this, okay?
Yeah.
You may put it to the left because the QR code didn't appear here.
Coming as far over as you can. Yeah, there you go.
Okay. Good like this?
Yeah.
Great.
That's good.
Okay, so let's recognize really an important point that most documentation on GitHub currently is README how-tos and API reference. The what and why aspect of what is usually connected to requirements are really less obvious due to a focus on the how and the implementation details. And another part is really that this conversation about requirements somehow has a chance to go into this bad direction that only regulations are needing requirements and that developers, they don't really want requirements and yeah, it's only to satisfy some certification body. So I believe that it's exactly the opposite, that the whole discussion should be with developers really understanding the requirements, and especially for the tools development and for the methodology, it's important that we look into how work with requirements before and while the code is written, not after. And with this regard, something that comes to my mind is a similarity between the culture of testing and culture of requirements. Some time ago, people just didn't want to test. You really had to very hardly argue that tests are useful, you need to do something, and then this community of extreme programming and agile movements emerged, and they explained, okay, you can do test-driven development. And so the most obvious thing that comes to my mind in this regard is that really before writing your failing test case, this red part of the TDD cycle could be complemented with the requirement. As easy as this if we think about the methodology. Now, let's talk about the mechanics. Let's say we want traceability and we want to do something with it, but then we are confronted immediately with large number of requirements. And usually we need to somehow partition the system. And the good news is that Linux is quite nicely partitioned. It has the system, subsystem, and then the source files. And here an important point connects to several other messages from the talks before, that Linux by itself is, of course, okay, it's a system, but it's always used by a user, by the end application. And the way this happens with a regulated industry or the space industry I'm familiar with is that you have a project specification, and then at some point in one of the aspect levels, there will be an operating system components, and then they have to trace down to the aspects of the Linux. So in this case, the operating system components would trace to Linux, Linux would trace to timers, and then to the source code functions. So this aspect of top-down tracing is very important. And finally, because requirements are somehow present in the GitHub documentation, in the Linux kernel, we need to find a way to distill them. It's not really about creating new requirements or really bringing something into the system that doesn't exist there yet. It's there, it's just not fully recognized as such. And currently, the biggest aspect that hides requirements behind itself is the API reference. But people mix that the interface specification is the same as requirements. Sometimes they are very close, sometimes they're not. And then another aspect that people confuse with requirements a lot is the design and architecture. So when we start to talk about not what the function does, but what really it does in terms of how it's implemented, which design pattern it's using, and some other aspects. The other aspects less conflicting with requirements. I think people are like easier to distinguish between them. Let's say the user manuals, how to build something, how to get something to work, and then license contributors configuration and all the aspects. So the exercise that we can all do is to grab a marker and find requirements in your favorite Linux subsystem. I could, and it's quite an interesting exercise on its own. So now about tools. Okay, I got StrictDoc, we have Bazel, we have many other tools. Currently, we have somehow a technology conflict and the gaps. We have big players like Sphinx and Oxygen and commercial tools like Confluence. And we have, as of today, I know 18 tools for requirements traceability of various maturity who are trying to complement these big players because they don't provide traceability. And this is more or less a successful synthesis in every project. So there are some hybrids that emerge. And the biggest topic is really even if we solve now the traceability with StrictDoc, let's say Bazel, how will this play with the other tools? And this interface topic is something that takes lots of time. So about StrictDoc, it exists since 2019 as a Apache 2 license. Some good stats already. It's a mature project, very heavily tested, some good quality. The original idea was, let's cut pros and codes into atomic nodes, give them unique identifiers, and then be able to link them together. And we got these capabilities for connecting all the artifacts together, like documents, requirements, source, test codes, test reports coverage. We can edit requirements on the web interface. We got a format that stores these so-called sidecar requirements, and also some interfaces for the other formats. In particular, we are working with this PDX working group to establish somehow equivalence that the documents can be converted both directions. And with this, I turn it to.
Okay, thank you. Now, to give you some evidence that you can use StrictDoc for serious work, I tell briefly about our internal use at Linutronix. So we have a Linux-based operating system called ELISA, which is targeted at industrial and embedded applications with a focus on sustainability, longevity, and security. And since our customers are now facing the European Cyber Resilience Act, we wanted to play a full certification of ELISA-based application against some security standard. We picked IEC 62443 for that. And the process that's mandated by that standard needs us to have requirements traceability. So we have to trace requirements to design items, to test. And for that, we would like to have a tool. And it turned out that StrictDoc fits our workflow best. Since internally, it's a workflow that is much like the kernel community does, based on Git, based on text reviews and such things. And another very important part why we choose StrictDoc was that if you look at the code, it's really well designed, it's well tested, it has a qualification package meanwhile even, and most notably our contributions were accepted in a very agile way. So this was highly motivating and we stick with it. And as outcome, got certified by TÜV March this year. And they mentioned several times that they like the StrictDoc approach. But if you are interested more in the story, I have linked a blog post about this. Now, a brief look into what is inside our technical documentation. So we started out with a template that was based on the ARC42 picture template, but we then enriched this with requirements, compliance metrics, a threat model, design items, test cases, test results. So StrictDoc can scan the test report and generate items out of it, and everything is linked. And everything is linked in a way that you don't have to duplicate code. So you can just use the robot framework code we have and link directly to that instead of rewriting the test case in prose. Another nice trick you see here is this compliance metrics. This is some interface between the external standard and our internal product requirements, where we explain how our internal requirements fulfill in combination with the external security requirements. And then during audit, we could just iterate over these compliance statements. And when evidence was needed by or requested by the auditor, we drilled down into the traceability graph and showed them the evidence. This worked out very well. Now the question is, can the Linux kernel community apply a similar approach? And the starting point now is what we have just seen from that. There is this ELISA Linux kernel requirements template proposal. And now for the rest of this talk, we just assume this SPDX tags get accepted. We know we are not yet there, but for a tool, we need something to hook on, and in this case, we use this SPDX tags. And the good thing about this that StrictDoc already can do exactly that. There was a Swiss company that requested such a feature, parsing custom tags out of source code. They used it for testing, but it can be reused. It can be reused for the case of ELISA here. We just need some enhancements in StrictDoc, and so we challenged ourselves: can we implement the missing parts? And yes, we can. If you are interested to look at it interactively, you can make a photo and follow the QR code. But I will go there anyway now. This what you will see now is a clone of the Linux kernel with all the content applied on top to get compiled requirements. And so we go to the hands-on part. What we see here is, as I said, the Linux kernel source code. Here is the tree output. And what do we see here? Yeah, there is some source code, memc, trace event C. There is some k-self-test. And I should now explain that the source code has the work of Gabriel applied. So we have already these function expectations patched into it.
Could you just increase the font size a bit?
Yes.
Thank you.
Is this enough?
It's a bit better.
Now we progress.
Thank you.
Okay. Gaps patches are applied. Then another round of patches is applied to have the tests from Alessandro. Okay, self-tests related to that function expectations. Another round of patches is applied to get this SPDX tags inside the code. This was done by ourselves, just on top of the function expectations. These are actually the tags that come from here. You have seen this in the previous talk. We have this rec ID and rec HK, rec text tags. These are exactly what you see here. And also, notably, we see the sidecar files here. Gabriel already mentioned them. We need some place for additional metadata, which is called sidecar in this context. And we decided to use StrictDoc's native SDoc format and syntax for this case. It could be done differently, but from StrictDoc's point of view, this is the most powerful option. Okay, and then you can run StrictDoc in CI. It should have GitHub Actions here. We install StrictDoc and run StrictDoc in CI. This is just this single command here, StrictDoc export. And the result is a nicely looking requirements document. So this is the output of StrictDoc. What is this?
Yeah.
So you see it parsed all the requirements from the source code. It merged them with the content from the sidecar files, and it retained all this traceability. You can see this in another view. There's also a traceability view where you see the graph behind this. Here we see that we have tests that relate to requirements. But we can also jump to source code. This requirement is, for example, related to this C function. So I can jump to the C function, and the same goes for tests. The requirement has a related test, and I can jump to the test, and I can also jump to the place in source code where the test is defined. Okay. And one more thing, since we are already here, StrictDoc cannot only compile this, but it can also apply validations. So you see here, something didn't meet the rules. Requirement has no related tests. This is something that we've hooked in through a plugin API. You can write custom validations against the traceability graph by using StrictDoc's plugin API, and then check whatever you like. I thought this may be something reasonable. You could go a step further and individually check their function expectation. I did also this, so function expectation 1 has no related test, is finding here. Yeah, this is how the validations work.
Small reminder on the tab.
Yeah. Okay. And one more thing is that we also support generation of these stable IDs and hash IDs. ELISA proposed this hash generation method, and this is now implemented inside StrictDoc. So we can run a StrictDoc manage auto assign command and calculate a hash over the combination of project name, file path, requirements text, and related source code. And if you continuously rerun this command, you get exactly that drift detection that you have discussed before. And yes, that's it. And let's go back to the presentation. Now, comparing this traceability model to what we have at Linutronix, it's much simpler. We have basically only tests that relate to requirements, and even that is somehow made up by us. I think this relation was not yet defined in the proposal, but we could define it if it's useful. This is how it looks on a source code level. You see on the right side Linux C source code, on the left side the sidecar files and StrictDoc syntax, and everything works on adding these UIDs, stable IDs, into the right place, and so StrictDoc knows which nodes to relate to each other. Okay, and that's already it. I have some remarks what could be done next. We could extend the proposal to talk about how and what to trace. So shall requirements maybe trace to tests and even to test reports. Would we want to have function expectations as an individual node? So that the function expectation becomes a child of the higher level requirement. Could be done, doesn't have to be done. If you want to individually link to tests, that's the reason behind. Yeah, we could mock up test code also with this SPDX text so that we don't have to state the information in the sidecar about tests. SPDX child and ref tags need some clarification. There we were not sure how to implement it, and used a StrictDoc native way to link things. Yeah, integration with things and kernel doc is obvious. This needs to be talked about. No solution on that. Then the kernel source code is a very large project. StrictDoc will take very long if you run over the whole code and also eat up a lot of memory. So this is some homework for the StrictDoc side to maybe involve in some redesign even. And yeah, I've shown you some validations. There the question is, can you think of useful validations and useful statistics? StrictDoc cannot not only do validations, but also collect statistics and metrics about your traceability graph. What would be useful? And that's already it. Now, ask us anything.
No questions, but in order to test the requirements, have you used the extra SPDX field in the test, or have you done it through StrictDoc?
This is done with StrictDoc methods. We have been, I could show, shall I show it in this source code?
I think that's actually where ref might be used.
Okay.
We might be able to use that too.
Yes.
The same way we would do it for like, later plans.
So we did it this way. We are not using the ref tag, but using this relation syntax, which is a StrictDoc mechanism. If we wanted to use tags, we have somehow to translate the tags into StrictDoc's relation model. Could be done, I don't know how useful it is.
Because you have a unique identifier for the node, and basically you put that identifier
Yes.
here to
Yes,
define the
this is how
relation.
you do relations. Exactly. You could, this is one relating one node to another, or we have another mechanism for referencing language constructs, for example. This is I like this a lot. I can point from StrictDoc to one specific function in C code by giving the function and the file name and function name. This way you could, if you want, keep the code clean of any annotations.
So basically, today, in order to define a requirement node, you scanned and as you read SPDX rec ID and SPDX between SPDX rec ID and SPDX rec end, that is a node.
Yeah,
So you have something that would scan the source
exactly.
file, right?
We passed the
For the test, you've done it manually, effectively.
Mhm.
For the test file,
Yeah, you should probably explain also the forward links, the link that you make forward pointing from
Okay,
the requirements.
this you see here. This is a test node, and here is what I just mentioned. From the sidecar, I give a pointer into the source code by saying relation, type file, role test, and value this source code file, this function.
in the function. Okay.
And the function is known then because we parse the C code with presetter. So StrictDoc is aware of the whole concrete syntax tree.
I was thinking if we need an SPDX formalism associated with the. So that,
Well, like I say, I think we need to play around with that, but I think ref would quite frankly, work,
Ref, yes, a good way to,
like that.
yeah, to trace test requirement.
Mhm.
And I was thinking if we need formalism to identify a test case.
We might want to look at that. We probably should pull in, Gustavo and some of the
Yeah.
kernel CI folk too here.
Because he needs to,
Yeah.
to define, I mean, he needs to define a test node, right? Somehow.
Yeah.
So if we had a formalism, like we do for requirements,
yeah.
if we had a formalism for test case,
Yeah, I think so.
then we can do it
Yes.
in a
Mhm.
cleaner way.
Yeah, I think so too. Yeah, you're right.
This was what I
Yep.
meant with annotating the test code.
Mhm.
Not bad, but the difficult thing here is that case self-tests by themselves give no, it has to be some executable program. There's no inner structure pre-described, and so when looking at G-test, for example, or robot framework, StrictDoc can be smart enough to recognize the tests because it has a certain syntax. But case self-test doesn't have a certain syntax. This needs annotation.
Yeah. You're effectively using a snippet effectively there for your line range as well.
Very similar to snippets.
It's a snippet.
That's how we converted them to the snippets.
That's what I was thinking it might be. Yeah, I think we've got something to talk about on Friday. Not this week, but
This Friday.
if not this Friday, next Friday.
No, but yeah, definitely, and
Uh-huh.
that's good.
It was
That's
very
good.
good.
It was something that because I don't know. I'm starting to think if we come to plan. I mean, if the V3 patch set was accompanied also by
This version,
this
that would make it more real in their
the
heads.
tooling, that would create like
Mhm.
a whole story.
What? I agree.
I'm there, I'm in Tokyo.
He-
We
He's still
can,
be here first, so we'll have all the right people in the room. So if we can get the version 3 up there, at least we can probably take and, you know, build on what they've got right now. I have too much trouble.
Yeah.
Mhm.
Okay.
Okay, then. I guess we conclude.